Thank you so much for having me. As introduced, my name is Jean-Ann Incorvia. I'm at UT Austin, and I'm really excited to connect with everyone on this call, especially with everyone in Italy. My family is from Italy, and I have family back there. So yeah, it's great to get to know you all more. So please, you see my contact information here. Please feel free to reach out to me after the talk. So like we have all been doing, it's good to upfront acknowledge everyone who's worked on these projects. My students are listed up top. Mashi, Thomas, Sam, San, and Leke are the main ones who contributed, and my collaborators in the second row from UT Dallas and Sandia. And the results I'm showing are supported by Sandia and also the US National Science Foundation. So what I would like to talk with you today about, first, I want to start out with a motivation for why we're interested in general in magnetism for computing, which Claudia nicely also introduced. And in particular, the devices we're focusing on here are called domain wall magnetic tunnel junctions. I then want to show what we've been doing on the experimental front to solve the challenges of these domain wall magnetic tunnel junctions for actually using them for these computing applications. And then thirdly, like the title of my talk, I want to inspire you about what kind of advanced cognitive computing functions these materials can provide to really transform how we do computing today. And then I will conclude. So there are many problems with traditional computing, especially when performing data-intensive tasks. There is a large memory wall between computing and memory access. There is energy loss when computers are idle. And there's also a large loss of energy when we convert from analog to digital information. And so this really motivates us to want to have devices that can both store information, perform computation, and can do so in the world without having to convert to digital information as often. And when they're off, not take up power. So magnetic materials are a very attractive solution to these problems. Firstly, they have fairly low write energy and write time compared to other emerging resistive memory elements. They're non-volatile, so they can solve this leakage problems, and they are compatible with in-memory computing. They're back end of the line compatible, so they can be fabricated, connected to CMOS. They have hardness for radiation, which is important for space applications, another big frontier for new types of computing devices. And then the focus of this talk is really on the complex features that they can have that can be mapped onto new systems. So all of the physics that have been introduced in the first two talks, so domain wall dynamics, oscillatory behavior, skyrmion dynamics, magnetic straight field interactions, these are things we can start to make use of for computing. So as Claudia introduced, one inspiration we take for how to transform computing is the human brain, which is very efficient at certain data-intensive tasks. So the brain is not very good at certain tasks, for example, summing really large numbers, which our computers are a lot better at. But then there are certain tasks that our brains are just a lot better than even supercomputers. So the canonical example is face recognition, where the brain can conceive 1,000,000 times less power than a modern supercomputer when recognizing a face. So why is this? Some reasons why is that the memory is distributed with the processing. So this is where in-memory computing comes in. We want our devices to both do processing and memory. This memory logic system is densely connected, so a lot of interconnectivity, and computing is able to be done in a parallel manner rather than serially, which also is a big benefit. But these are just really chipping away at the start of what our brains can do, and there are a lot more advanced biological functions that I will touch on, a couple of them in today's talk. So these are just some examples. There's many out there of magnetic computing state-of-the-art, people working on racetrack type computing, stochastic tunnel junctions, spin torque oscillators, and skyrmion computing. So for this work, we are focusing on the computing device shown here, which is called a 3-terminal domain wall magnetic tunnel junction, or DWMTJ for short. So you can see here in the picture what it looks like. We have our for people of magnetism, very basic tri-layer stack of our heavy metal tantalum underneath, our cobalt iron boron domain wall track with magnesium oxide on top. And then we have a pattern magnetic tunnel junction on top that can read out the state of the this domain wall position on either side of the tunnel junction. And we could imagine this device also working with fermions as well. So these domain wall MTJs have shown a lot of promise for both in-memory and neuromorphic circuits. There's been work from myself on small circuits, also groups working on synapses, where if you make this tunnel junction large, then you can imagine having analog number of states, and then hooking them up into all-spin neural networks. But for using these domain wall MTJs for these neural networks, or for all these types of computing, and in general for this type of tunnel junction-based analog computing, there are certain challenges which we really need to overcome first. And one of them is that these type of devices often have high current density and low TMR, so the tunnel magnetic resistance, the on-off ratio. Here's some examples from our previous work. The resistance of our tunnel junction was around, this TMR swing was around 10%. Here's another group from 2018 where when they were trying to do this majority type logic, after patterning this cross structure and this tunnel junction on top, they got around 15% TMR. And there's been work where people have shown up to around 40% TMR after patterning these type of tri-layer structures or three-terminal type structures. So this is the first thing we sought to overcome. So here are our prototypes of these domain wall MTJs, which we patterned down to 250 nanometer feature sizes. So here you can see this domain wall track, and the width here is what I'm using to define the feature size. And this is our tunnel junction in the center. And so here we use this thick heavy metal layer underneath of tantalum to provide spin orbit torque switching to really lower the switching current density, so we can now reliably operate the devices without burning them. And we then have improved the patterning process to be able to maintain the TMR after patterning. So these films were grown by Applied Materials and then patterned at UT Austin and tested here. So here is some example tunnel barrier resistance versus magnetic field of the patterned devices. Here's 6 example devices. So you can see the unpatterned TMR was around 168%, and after patterning, on average, around 170%. And similarly, our resistance area product, which really tells us the quality of the junction after patterning. So before patterning, it was 35 ohm micrometer squared, and after patterning, around 29 ohm micrometer squared. So we're able to get high TMR after patterning, and the highest TMR, you're really close to the highest TMR, which is around 200% that you really expect for perpendicular anisotropy tunnel junctions. So now that we have these robust devices where we can operate them reliably and we can maintain the TMR, we can now start to do statistical studies of their behavior, which is very important for using them in devices. So here I'm measuring the tunnel barrier resistance versus applying a voltage pulse. Here's what I'll come back to exactly how it works in a second, but what you can see here is that in these left plots, where we have something like this device shown here, where we don't nucleate a domain wall, we just have a unidomain on the bottom. And so you can see here we have one domain, say one direction, the output tunnel junction another direction, and then we apply current to switch between the in and clock terminal. So with these PMA junctions, when you apply current, you're going to nucleate a domain wall, and it's most likely going to just nucleate at a random pinning site and then switch. And so we see, as we expect, that if we don't control the domain wall position, we get this binned but random and quite large range distribution and our depinning voltages to switch the device. But then if we carry out this protocol here, so we again, we start out with our saturated unidomain bottom layer, and then we apply a current at an Ørsted field line here to nucleate a domain wall underneath. Now we have a single domain underneath this wire here, which we can then switch with current back and forth to have our device operate. So here we apply a current between in and clock here, switching back and forth, and then we can switch the domain wall over and therefore switch the resistance state of the device. And so we can repeat this. For example, here is repeated 10 times, and we can see that we maintain our TMR, and we get an average depending voltage about 10% variation. And so now that we have this 10% variation, we can start to do things like build reliable circuits with these devices. Here is a 2-device circuit where the output of the first device is sent into the input of the second device. I think maybe for interest of time, I'll just skip going over this in detail, but you can read the paper to learn more about it. Because I want to get on to the third part, which, so we are continuing to tackle the challenges of the experimental use of these RAML FPGAs for computing. But at the same time, we want to think about, well, what are these good for? Why do we want to do this work? And we really want to take advantage of the complex physics present in these RAML FPGAs and in general in magnetic materials and devices for computing. So the first thing I want to show you is using lateral inhibition for soft winner-take-all circuits. So when I talked about brain-inspired computing, the basic building blocks of a brain-inspired computer are neurons and synapses. So for those of you who might be less familiar, you can have a pre-sending synaptic neuron and then a post-synaptic receiving neuron. So these neurons are going to take in a potential and then eventually fire. And then the connectivity between the neurons is controlled by the synapse, which in the artificial world, we usually encode using a variable weight resistive device. So we can create both the neurons and the synapses out of RAML FPGAs. For this talk, I'm just going to focus on the neurons. So to create the neuron effect, similar to what Claudia showed for the skyrmion track, we can have this RAML track, and then if we offset our tunnel junction to one side, then we can get a neuron-like behavior. And it can act as a leaky integrate and fire neuron. So this is in simulation, using micromagnetic simulations, looking at the domain wall position versus time. So when we apply a current pulse, we integrate as the domain wall moves across the wire, so it starts going this way. And then if we take away that pulse, an external field, for example, can allow the domain wall to slowly drift back to the other side. And this is something that's seen in biology, that we want our neurons to be able to relax back to the original state on their own when they're not being used. And so we can implement this leaking behavior, so we have integrating and leaking. And then once the domain wall passes under the junction, that's when it fires. So here we used a field leak. We can also do other tricks to leak. For example, we can pattern the wire into a wedge shape, and then we can have a shape anisotropy leak. And we've also explored this, that it works also in simulations at room temperature. So another bio-inspired behavior that is very important to learning is called lateral inhibition. And this is the idea that if you have one neuron winning out, it should suppress the behavior of nearby neurons to prevent them from firing. And it's very important for reducing errors and increasing the efficiency of a neuromorphic calculation. And it's usually implemented in artificial neurons and synapses, or in current like CMOS-based implementations through bulky peripheral circuitry. So here's an example circuitry of a CMOS winner-take-all circuit. So lateral inhibition can lead to winner-take-all, where only the leading neuron is one that wins out. So that's called winner-take-all. So in this CMOS circuit, it requires about 5 transistors per neuron. So if you had 200 neurons, this would be 1,000 additional transistors you need to implement this lateral inhibition behavior. But it has large benefits. So in this example circuitry, it was able to have the computing power of 2 layers of the neural network, which is a single layer. By also including lateral inhibition, it really just increases the efficiency and accuracy of the circuit. And so here, we want to achieve device inherent behavior that we could then implement these behaviors without having to have this large area overhead. And so we can do that with our neuron tracks because we can make use of stray field interactions. So here's what we can imagine. These RAML FPGA neurons are set up side by side, such that the center one, say this one got more current applied to it, it's winning out, so it's doing well, it's farthest ahead. Then we want this stray field to impede the motion of the other one so that they don't fire. And here is the setup of the micromagnetic simulation using Mumax. So here are two. We start out just looking at two side-by-side neurons. And so they have width W and the spacing S. And then they're going to have this stray magnetic field from one to the next. And so we can see the effect happening here. So this is just a simulation snapshot of the two side-by-side neurons when we include stray field interactions and if we don't. So if we include stray field interactions, and then this dream wall has gone ahead, and this one has gone this far, versus if this one's not ahead, then this one can get farther. So when this one's ahead, it prevents it from getting as far. So we initially saw this in our simulations for very narrow spacing, for 6 nanometers of spacing and very narrow wires, 32 nanometers wide. And we thought, okay, this could be interesting, but it's actually useful. You know, it's really hard to get things that are spaced 6 nanometers apart. But we can see here where neuron 2 is doing velocity as we apply current to neuron 1. So as the current to neuron 1 makes it get ahead, neuron 2's doing velocity goes down. And we also saw a fairly modest effect around 72 meters per second to 58 meters per second. So we really sought out to understand this effect better and see if we could make it an actually useful effect. And so when we looked in more details, we really found that we can tune this effect quite widely, and that it really has to do with how the stray field affects the domain wall angle of the neighboring wire. So here we used width equals 50 nanometers in our simulation, and the thickness of our cobalt iron boron that we're simulating is 1.5 nanometers. And so we can get this plot versus wire spacing. So this is, again, 2 neurons side by side, and this is the velocity of the second one being inhibited by the first neuron. And so it's easy to see just if you look here. First of all, if you have non-inhibited, if you don't include the magnetic stray field interactions, then we just get domain 2 at a certain velocity compared to the spacing like this. If we start to include the magnetic stray field interactions, then and the spacing is very wide over here. We have steady motion of the domain wall. And then when the spacing gets narrow enough, the stray field becomes large enough that it sends actually that domain wall into Walker breakdown. And so you can see that here, that the position versus time is going this wiggly, it's going through Walker breakdown. And so by tuning the spacing, we can then get to this transient region where we're between precessional and steady state motion, and we actually get a great reduction in the velocity of the neighboring domain wall. So looking into this in more detail, you can see here for 4 different spacings, 30, 60, 90, 120 nanometers. You can see that when you have inhibition, you can get a small effect, a bigger effect, and then you get this sweet spot where you get a really large inhibition effect, where you get this big decrease in the position versus time. And then if you go even larger, it starts to get less. So over here, we can define the lateral inhibition percentage as this difference in the velocity. And we can see there in this scenario at 90 nanometer spacing, we can get up to 75% lateral inhibition. And so we've been able to achieve this in very feasible size wires, and we don't have to go to these very narrow spacings, which we might have initially assumed. This is more information about how the domain wall angle is being set by the stray field interaction. So as we know, a domain wall has a certain angle above the domain wall propagation direction, phi here. And so here is a plot so the black curve here is phi as it just goes through Walker breakdown. So as it's moving in space, it's also changing its angle. And then for these different spacing between them, we can see that we're setting the domain wall to a certain angle along this curve, and that is what's going to determine its velocity. And so this makes sense from the equations for velocity of a domain wall in the steady regime and the Walker breakdown regime. It depends on this phi. So we can further tune the lateral inhibition using other materials parameters. So for example, here we explored changing the saturation magnetization and also the anisotropy energy. And so here's versus wire width for 3 different saturation magnetizations, and for this was for 3 different wire widths with varying the anisotropy energy. And so we can see we can get up to as high as 90% lateral inhibition by tweaking both MS and KU and the spacing. And so we can drastically reduce the velocity of these nearby domain walls when the most activated domain multi-J is winning out. Okay, so that was in 2 side-by-side domain wall tracks, but you know, as I showed how we want to array these as a neural network, we want them to have many domain multi-J's side by side. And so again, we were not sure at first whether this would work because would the stray fields just cancel each other out? But what we found we can do is by having 2 spacings, S1 and S2, we can then have a non-canceled out stray field interaction that can implement soft winner take all. So that means that the fastest ones win out and the slower ones get even slower. So the fastest ones fire and the slower ones, the ones that are getting less activated, don't fire. So here is just, again, you can find a sweet spot by tuning these spacings where the center neuron here is a little bit inhibited, but over here between its neighbor neurons, it's very inhibited. And here we simulated 1,000 side-by-side neurons. This was not in micromagnetics. We benchmarked our model against some micromagnetics in order to build it up into a larger array. And we ranked them 0 to 1,000, and they had various domain wall velocities. So this was their intrinsic domain wall velocity. And then after including inhibition, we can see that all the very fast ones, their velocity is fairly unchanged. And then as they get slower and slower, the really slow ones get a big reduction in their velocity. And so we can really get this contrast enhancement, which is important for computing. So our colleagues at Sandia set up a learning classification simulation using these effects. And they tested the MNIST classification data set versus lateral inhibition coupling constant. And they actually found that if there's very weak coupling, the classification actually goes down. And also if there's very strong coupling, if they only have a hard winner take all where they won that's fired, that's being activated the most wins, that also isn't so good. So we actually do want a soft winner take all, which you can really tune now by looking at these interaction parameters. Okay, so I went over time, so I think I should just stop here. I have another BrainInspired effect that you guys can read the paper on. I'll just briefly mention it. So we also have been looking at another BrainInspired behavior called edge-relaxed behavior, and we're showing in simulation that this can be very useful for data set adaptable circuits. So this is using the same domain wall MTJ, and we're making use of the fact that the domain wall could spend time over here on this side of the device, or it could spend time over here closer to the firing region. And this is very similar to how muscle neurons work, where if a neuron gets activated more often, then it's more likely or more easy to fire. And if it's activated less often, it's less easy to fire. And so as you can expect, this could be especially beneficial for repeatable tasks. So if your neuron is trying to recognize similar images a lot, then we might want to make use of this relaxed versus edgy behavior, which we can inherently, again, get in our domain wall MTJs. So maybe I'll stop there, but you can read the paper that's coming out in IEEE Magnetics letters. So I'll just go to the conclusion here. So I hope that you've been inspired about the BrainInspired behaviors and device inherent behaviors we can achieve with magnetic devices, which could really bring us to new computing paradigms and ones that can take inspiration from biological neurons.